All right. Welcome back, everybody. Our next speaker is Deniz Memis. The talk is called Context-Aware Software Stacks for Mobility, an overview of the Composive.ai. Deniz holds a bachelor in electrical and electronics engineering and a master degree in engineering and technology management. As a software developer at Eteration, he and his team are developing solutions for model-driven complex autonomous systems such as autonomous driving. Deniz has provided us a pre-recorded talk, which I'm going to play now. And Deniz is also here in the meeting, so you can ask him questions afterwards.
Hello and welcome everyone. My name is Deniz Memis and I work as a software engineer at Eteration. In this presentation, I will talk about our project called Context-Aware Software Stacks for Mobility, which we have recently started. This project is an initial step of our final action plan of developing a family of products that we call Composive.ai, of which I will provide an overview in the end. Taking a look at the outline, first off, I will briefly describe the background information and the research we have conducted. Then I will follow it by elaborating our approach to context awareness and adaptivity problem for autonomous driving and how we are planning to design and develop our software stacks. To talk about the background, it is known that experienced human drivers are very good at adapting to different driving conditions and environments. Because they are able to transfer their previous knowledge to the current driving context. AD software, on the other hand, being very complex systems of interconnected modules that are both stochastic and deterministic, they may perform poorly, especially when they are in a context they are not designed and trained for. Starting with DARPA challenges, statistical learning methods have been used vastly in implementing very successful AD software. The quality of these solutions depends heavily on their statistical models and the training data. These systems are very good at learning, perceiving, and adapting to the environment. However, there are still many challenges to this learning process, as the huge learning data required to train these models lead to much difficult to explain biases. And especially in driving, there are certain edge cases where the algorithms may come up with unexpected results. In the end, these systems have very little or no contextual capability or ability to abstract knowledge or reason about a drive. More sophisticated machine learning methods, such as deep neural networks, learn from the data more cleanly, so to say. However, it requires careful engineering and modeling to do this efficiently. DARPA recently announced the next AI challenge, and they are focusing their investments on a third wave of artificial intelligence. And these are the machines that could understand and reason in context. From a high-level perspective, there are two major approaches to autonomous driving problem in terms of system design. First one is a modular approach, where AD can be summarized as a set of core modules, each responsible for a separated concern, such as perception, prediction, planning, and control. As opposed to modular systems, end-to-end driving generates ego motion, which is the 3D motion of a camera within an environment, directly from the sensory inputs. There are supervised and unsupervised models to achieve this. However, each has its own downside. For example, supervised models could be trained offline. However, when they are deployed to a real-world scenario, they may perform poorly because they have generalization problems. And unsupervised models should be trained online because they are not trying to imitate a human driver, but trying to learn the optimum way of driving themselves. And this online training requires so much time and effort. And even though they are very promising, there is no real life implementations yet. In our work, we are focusing on the generic AD software stack starting from perception and down to planning. The model-based approach is applicable to modular system, where the system design could be adapted as necessary by the virtue of their modular nature, whereas end-to-end systems are less inclined to be interfere with because of their black box type of nature. Most of the modular AD stacks are based on robot operating system. And in our concept, we characterize these stacks as context-sensitive modules. And as ROS-based data flow systems, they could be models. And moving onwards, the implemented models could be used for adaptation purposes within the different contexts. In the emerging machine learning technologies, I want to talk about two new approaches. First one is contextual AI. Contextual AI is not a specific algorithm or learning method, and it is defined as a human-centric perspective and approach to artificial intelligence that will increase the human control and customization over the systems. This approach allows context-aware systems to provide tailor-made and specific services and solutions under varying conditional changes. The second one is explainable AI, and explainable AI or XAI produces more explainable models without compromising learning performance, and it enables humans to understand, therefore trust, manage, and control the system of models. I didn't want to explain these two concepts very in depth. However, I want to talk about how we can benefit from these approaches. Is that we will get to know and possibly formulate more efficiently the relationship between the decisions have been made by the system in the end and the structure of the system in terms of models. Moreover, thanks to the provided human readability and customization ability, we would have in-depth knowledge of which feature sets of which inputs are affecting the final decision and how they are doing it. We believe that this type of exposition of such connections will play a major role while making a definition of a context in our work, and will enable us to compose the software stacks based on the future context relationships and associations. To give an example of context variation, just thinking of a historical city as Istanbul is a great example because the frequency of how the context change is very high. In other words, it can be said that the urban driving in a well-organized city versus a city with unorganized narrow roads and streets with no traffic signs or lane markings, for example, will require training with completely different data sets and probably using different models. For us, the context is dependent on all the sensory, environmental, and behavioral data. When the action of driving takes place, all these inputs interact with the system and change the system's behavior. Therefore, we define the context as a set of all inputs from the sensors, for example, the LiDARs, cameras, radars, and additional inputs from the environment, such as traffic signs and the people's behavior, whether it's another driver or a pedestrian walking on the street. Based on this definition of a context, the context awareness for AD involves the semantics and the modeling of the context for which AD software is trained and designed, and using this information about the context to adapt how modular AD softwares perceives, predicts, and acts in the ROS-based modular pipeline. Our goals in Composive.ai, as Herbert Simon stated in the Sciences of the Artificial, the adaptation is actually computation. And we would like to define an existing state and a desired state, and we would like to find a correlating process that will erase this difference between these two states. And this process is, in our work, starts with abstracting contextual knowledge for autonomous driving and modifying the runtime code based on these models, as opposed to the code-first black box systems. Since our work focuses on ROS-based modular AD software, I want to talk about why this is the case. This is because of the simple fact that almost 90% of the modular AD software stack is based on robot operating system. Each node in ROS, as you can see in the figures, responsible for a single and modular purpose. One node could control the LiDAR inputs. Another one is for camera, and one node maybe just handling the simple processing of the sensor fusion. And each node can send or receive the data to other nodes using topics, services, and actions, which are the definitions in the other definitions in the ROS ecosystem. A full robotic system is comprised of many ROS nodes that are working in coherence with each other, and due to its distributed nature, ROS system is highly modelable. There are approaches that resembles to our approach that are model-based. The first one is Robomosis, and Robomosis enables the composition of robotics application with model-driven methods. And following the Robomosis approach, the MROS, the meta control for ROS2 systems, trying to modify the robot control architecture at runtime using ontology reasoning with the same model-based approach. In our work, we are exploring a model-driven approach to define models for the proven open source AD frameworks. AutoWare is our primary use case. And on the left-hand side, we are breaking down an existing stack to come up with an initial model conforming to a meta model. And on the right-hand side, we are composing the models generated in the previous stage as a response to an adaptivity problem. And our final goal is to deploy these adapted composed stacks to a runtime platform with lifecycle management capabilities, such as launching, starting, loading, or unloading the stacks as necessary. Since I mentioned AutoWare as our primary use case, I want to briefly talk about AutoWare. It is a popular open source software project. It provides a complete set of self-driving units. They have a successful implementation of the modular AD stack, and they have a proven performance record with the embedded systems. We are currently working on creating the modeling framework that will capture a running AutoWare system. As extracting model is the first prerequisite in our solution, at this stage, the context detection doesn't need to be depicted by any machine learning methods. It can be considered as an algorithmic rule-based or a simple definition of a context, where we may even declare the context. Because the first objective is to lay down the models of the existing stack, so it could be later be at our disposal in a certain repository for software stack composition operations. And second objective is to formulate and create the context detection models and algorithms which will provide the information about the context variation, and algorithms and models will make use of the sensory input data, and they will help adapting the active software stack. In the figure, there's a very partial representation of how AutoWare ROS graph is constructed and how they are related to a specific AD module, for example, perception. On the right-hand side, there's another illustration of how we are aiming to achieve modeling this ROS graph in terms of entities and associations with respect to our modeling approach. And as a result of our modeling efforts, it will be possible to dynamically adapt these models to better address a given context. When the complete modeling work of AutoWare is done, we will have a clear set of models of both node functionalities and the information flow between the nodes. This figure is not depicting a complete set of done stack modeling. However, conceptually, it describes how the main building blocks of the ROS graph could be identified and grouped as a modeled nodes, topics, and other entities. This potential stack model is mapped to a context that reflects the condition of that specific context. And since we are proposing context detection models and algorithms in future, these conditions will reflect the context-specific training data. We also believe that this approach is not limited to autonomous driving. The applications in the mobility space exist in many different domains. Connected cars and smart cities make use of cloud-based services and other innovative human-computer interactions. The same context-based adaptation techniques can be applied to model-based software application within these domains. For example, the service orchestrations based on BPMN-like flows or component-based user interfaces that we can break it down to the view flow-like structures would also benefit from this solution. Composive.ai will deliver our components and tools for building adaptive software stacks as open source software. Looking at the roadmap, we are laying down our architectural definitions and working on the models and algorithms part. As I said earlier, we have recently started. In the first 3 months of the next year, we are trying to come up with a release, a version 1 release in the 3 verticals. And right now we are conducting our case studies. The first one, as I talked about, the modeling studies based on open source modular AD software stack. Once we are done with that, we will start our second case study, and we will test our model-based approach in a real-time environment using a 1/10 scale RC car that conforms to F110 specifications. Thank you for listening and your attention. We would be glad to answer any questions.
Thank you very much, Deniz. Deniz, you are here with us, right?
Yes, correct.
Hi, welcome. Thanks for the talk. Do we have any questions from the audience to Deniz? I would have a question. You mentioned the Robomosis project. I would be interested to know which parts of Robomosis do you actually use or have a relation to? Is that Papyrus or?
First, I want to say that I'm not alone here. We are here as a team. Our chief scientist, Mr. Dai, is also here. Maybe he would like to step in and give better answers.
It's not. So I guess there's another question too with Robomosis, Marco. We have looked at Robomosis to, for example, reverse engineer an AutoWare model, the actual software using their reverse engineering tools, also through manual implementation of the whole graph with Robomosis contexts. Of course, it's based on EMF and we use the existing release there. It has some challenges in terms of, for example, being able to use that model in a runtime environment, especially on an embedded platform. So currently, we are also evaluating, for example, other approaches, and of course, building our own DSL for the actual ROS graph that could run on the actual vehicle, like Deniz said, this F110 platform. So I think what we're hoping that based on the outcomes of these use cases and the case studies, we'll be able to put out a modeling language and a DSL that can be released under an Eclipse project sometime in the next few months. So that is the current target.
Sounds good. Thank you. We have a question in the chat. Which kind of languages are you considering or using for the modeling? Flow languages were mentioned, as well as BPMN. Variants of that. Have you considered any automotive languages like AADL, ASTADL, etc.?
Thanks for the question, Yuva. So that's actually a very good point that you have raised. We have found actually the initial implementations of this adaptivity problem. We have tried in different platforms. The first one was a BPMN-based flow. And that we could adapt the actual process during the execution of the actual instance of the workflow. And this has been deployed to multiple production sites for typically on cloud-based services such as, for example, a financial transfer and detection of a fraud during a financial transfer, that it can adapt itself to these cases. The whole idea was there that you don't have to foresee all possible cases, that you may have sort of different fitness functions for a flow, and each one of the components in the flow that you can find a better match. For example, whether you interrupt the flow, or in some cases personalize the flow, that this is a valuable customer. So it is definitely applicable. Another area that the same approach has been used was there are some I guess subset of BPMN can be used to define, for example, a user interface and the forms in a user interface with user actions, and that these could be also combined with some microflow technologies for building user interfaces. We have used these examples to build mobile applications and dynamically change the user interface based on the context. In the current automotive applications, we are focusing on specifically ROS-based implementations, and we are not building this AD stack from scratch. So our complete focus is using what is available, and AutoVer is obvious use case here. And we have looked at Apollo, for example, but some of the reasons that Andy already mentioned, we see AutoVer as a more critical use case in our case. And we evaluated Robomosis, and there's also other work, for example, from Fraunhofer, that uses a ROS-based model for care robots. I think that's also some Eclipse-related technology based on Xtext. So there are some multiple different DSLs and modeling technologies that Eclipse already provides that addresses the ROS space. So we haven't looked at AADL or ADL languages. We are more focused on what is so available in the ROS space specifically. Our criteria is that this should be running in a with a very lightweight runtime framework on an embedded environment, and that we should be able to easily build that context fitness into each node and also the complete system graph, so that we can reevaluate the fitness function during runtime continually based on context inputs, and find the optimal fitness of the whole graph that fits the context. I don't know if that answers, but we should be able to, I know we're kind of talking about concepts now because it's the really start of the project, but some of the use cases and live demos should be available in the next coming months.
All right, Naci, thank you very much, and Deniz as well for the presentation and this discussion.